Good morning. It's a pleasure to me to present you Alejandro Suárez Mascareño. I know most of you know already him. I just start from he was here doing his PhD together, under the supervision of Rafael Rebolo, the director of the ISD, and myself, on the more or less the same topic that he's going to talk today. So he was trying to find low mass exoplanets orbiting solar type stars. And during his PhD, he was already discovering a few very low mass exoplanets of only a few Earth masses. So this is really an important result. And I think today he's going to present what he's doing now. He's now at the Observatoire de Genève, together with a very big and important group there, especially on the radial velocity searches. And I think today he's going to talk about what he's doing now or what he's expected to do in the future.
Okay, hello everyone. As he said, I'm going to talk today about what we do to look for low mass exoplanets and what we will need to do to get to Earth, actual Earth-like planets. Right now, in the field of exoplanets, we know around almost 4,000 extrasolar planets, around almost 3,000 stars. In 600 cases, we have multiple systems, most of them with 2 or 3 extrasolar planets, some of them even resembling our solar system. Of those 4,000 exoplanets, 700 approximately are probably rocky exoplanets. 40 of those rocky exoplanets might be habitable, considering a very optimistic definition of habitability, and we know basically one actual habitable exoplanet. The search for extrasolar planet started in the early 90s with the discovery of 2 exoplanets around a pulsar with that name that I never remember. And then we have had basically 2 big branches in planetary discoveries. One, the radial velocity branch that started with the discovery of 51 Pegasi b, and then basically exploded with HARPS, and it's now ready to transition to Espresso that should be able to detect Earth-like planets, and then the transit survey that started with the discovery of the first transiting exoplanets, then exploded with Kepler, and now it's about to transition to TESS that should be releasing the first candidates, I think, today. And my specialty is radial velocity, so today I'm going to talk about radial velocities. In case not all of you know, to detect a planet through radial velocity, what we do is we measure the change in the velocity of the star, measuring the Doppler shift of the spectral lines, and the star changes the velocity because the planets orbiting around it pull the star with their gravity, the same way the star moves them around them. Then what we do to measure that velocity most of the times is do a cross correlation, which is basically an average spectral line at the velocity of the star that we compute, comparing the stellar spectrum with a template with a few thousand spectral lines at laboratory wavelength. So we move the template, and we start building the average line, then we have it, we measure the minimum in the line, and we have our velocity. Most of my work has been done on the HARPS and HARPS North spectrographs, which are the best in the world for radial velocity measurements. They are in the one in the 3.6 meter telescope in La Silla, and this is HARPS, and HARPS North is in the Galileo telescope in La Palma. Both are more or less the same instrument with a resolution of over 100,000 on almost all the visible range. Both are thermal pressure and mechanically isolated to ensure long-term stability, and both have proven to have instrumental stability better than 1 meter per second. To achieve this, we need a very, very precise wavelength calibration, and also we need to track the drifts of the lights on the CCD during a night. So what we do is basically we use a thorium-argon lamp to calibrate the wavelength, and then we do a simultaneous calibration during the observations. So at each exposure we have the stellar spectrum and the calibration spectrum happening simultaneous to track how the light is moving and then correct it. With the thorium-argon lamp, we managed to have a precision of around 20 centimeters per second. And with the Fabry-Perot that came really late, we managed to get 10 centimeters per second. Usually we use both because the Fabry-Perot cannot perform the absolute calibration. So usually you will do this one with this one simultaneously, and then this one during the exposures. And now I'm going to explain, well, no, I'm going to explain this before. Okay, this is the radial velocity time series that we can get. This is what is considered more or less a standard radial velocity star. And we have like 14 years of measurements with like almost 1,000 measurements, and the dispersion of the measurements is just 1.2 meters per second. And that 1.2 meters per second includes the instrument, the dispersion caused by the instrument, the photon noise, the stellar activity, and the possible planets in the data. It's everything together. It's just 1.2 meters per second in this case. So this tells us that the instrument actually works as good as we expect it to work. And now I'm going to show how we detect exoplanets using my last result as an example. This comes from a project led by the IAC with the collaboration of the University of Geneva, and it's basically the first discovery. And it's around this star. This is a K2 dwarf, around 80% of the mass of the Sun, with a rotation period that was estimated before this work at around 33 to 40 days. And it's located in the Sagittarius constellation, but it's not bright enough to see it just at plain sight. With this star, we managed to get this radial velocity curve where we have an RMS of the observations of less than 4 meters per second with a typical uncertainty of less than a meter per second. We observed it for 14 years, and we are still observing it. And as you know, for the previous star that I showed, the instrument and the noise and everything usually only accounts for around a meter per second. So if we have 4 meters per second, the probability of having significant physical signals in the data, it's really high, planets or stellar activity. So we start to look for periodic signals that we do basically using a Lomskargel periodogram, which is a tool designed for unevenly spaced time series, where we basically feed a sinusoidal signal to the data. We calculate the change in the chi-square, and we normalize it. And what you get is basically a it's something similar to a Fourier transform with a peak at the position of the periodicity. This is what happens when you have like a very high amplitude signal with even like thousands of data points. This is a synthetic signal. But once you go to a real signal similar to that, it still works, even if you have gaps in the data. It doesn't matter. It works for mostly any kind of time series. That's the reason why we use it. It has one main limitation, that it works under the assumption that there's one dominant signal. That up to now that hasn't been a huge problem, but for the future, I'm talking about this later, it's going to be. So we do that for our data, and we find these three significant signals: this one, and this one. What we do here is we find one, we model it, we subtract it, we analyze the residual, we model that, we subtract it, we go to the residuals until there's nothing significant in the data. Our three signals are this one, 3.5 day signals, almost 17 days and 36 days. And now the question that we need to ask ourselves is, what's the origin of these signals? Do we have 3 planets? Do we have 2 planets? 1, 0, because planets are not the only thing that cause a change in the radial velocity. Stellar activity can be a really powerful cause of radial velocity variations, and there are many different phenomena that can cause it. You have the stellar oscillations that last for minutes and usually cause changes smaller than a meter per second. You have the granulation that usually changes in like a day to 2 days, and it's also 1 meter per second. So these two, for this data set, are not really the important ones. Also, we have no signals in these timescales, but then you get the rotation signal that it's caused by spots and flash on the star, because the spots block part of the light. So when you have a spot in one side, the contribution of the light on the other side gives you redshift, and also when you have flash, you have inhibition of the blue shift, of the convective blue shift, so you have an apparent redshift, and they can cause signals that go from like less than a meter to more than 300 meters per second. And then you also have the cycles, like the cycle of the sun, that cause a change in the convective blue shift of the surface along the cycle, and can cause variations from less than a meter to up to 10 meters per second. Now that we know this, we need to find a way to tell that our signals are some of those, or are not any of those. So what we do is we go to spectroscopic indicators. In this case, I'm showing you the variations in the emission of the calcium H and K lines of the star, that usually the emission is caused very near flash in the chromosphere of the star, and as the star rotates, you see the flash or you don't see them, so the emission level changes. Here is the time series of this data, and the first thing is that there's a very obvious variation that has 6.6 years that we identify as a cycle, similar to the cycle of the sun. And then there's a second signal here that it's 35.7 days. And we identify that as the stellar rotation. And if we go back, this is 35.7 days. And also, if you look at the shape, these and these are almost perfectly anti-correlated. So first thing we can say now is that 35.7 day signal, it's not a planet. It's probably the signature of the rotation of the star. We have to be sure about the other two. So what we do first is check if this fits with other stars. This is the diagram of the relationship between the rotation period and the mean activity level, chromospheric activity level of the star. And if we draw the three signals, you will have this one, that it's perfectly aligned with all the other stars, especially if you go to only K-type stars, which the same spectral type as our star, it fits perfectly, and the other two don't. Then, if you measure the amplitude of the signals, all of the signals were smaller than 3 meters per second, which sadly, it's what we will expect for a star of this activity level. So from here, we don't get too much information. We get that the 35.7 day signal is consistent, but like every low amplitude signal will be consistent. The next thing is that we measure the stability of the signals. There's one very big difference between stellar signals and planetary signals, that planetary signals are always there. The planet doesn't change in mass, it doesn't change in period, it doesn't change, the signal doesn't change in phase. The planet orbits the star over and over and over again. But flash and spots come and go. So what we can do here is that we measure the significance of the detection of our signals as a function of the number of observations. If the signal is a planet, what we will expect is that it always increases, because the signal is always there, so more observations means more significant detection. If it's not a planet, it can change, because the star can go to a low level of activity and the signal can just disappear, or amplitude can go down, and that's basically what we see here. These two signals go up and up all the time, and this, I remind you, it's 14 years, so the signals have been there for 14 years with the same amplitude inside our error bars, but then for the 35 days it seems to go up, but then it goes down, and up again, and the amplitude changes dramatically. It goes from 1 meter per second here to 3 meters per second here. If we do it like corresponded with like time, what we see here is that basically in this phase, well, first the rotation signals seem to be there for 8 years, but then here the observational strategy changed. We started having a really high density of observations. Before it was having like 30, 20 observations every year. We started having 30, 40 in 3 months. And when we started doing that, we saw that the signal was not as we thought it was. So this is further evidence that this is a stellar signal and these two are not. And then, knowing this, we do a global modeling of the whole system. We model planets using Keplerian signals. We model activity using Gaussian processes that take into account stochastical variations and the decay timescale of active regions, and we get basically our 2 planets with the same parameters that we had with a very straightforward chi-square modeling, and our rotation with the same parameters that we had. So we are happy with this. We have 2 planets, one that it's a big super Earth, maybe small Neptune, it's unclear, and another one that it's smaller than 6 Earth masses. Sadly, these planets are not very good places to go and have holidays. You will have, like, in the coldest one, you will have 20 times the radiance of the Earth. But as the inclination that we measured is compatible with 90 degrees, they might transit. I know there are at least 2 surveys trying to find the transit, and if they transit, we will be able to analyze the atmosphere of those. And it's not that common to have atmospheres of such small planets. These 2 planets fit like there in the diagram of detected planets using radial velocities. I only included here the planets with masses measured. If we include the transits and the mass estimations, this will be much more crowded. And our group, with the collaboration of some people in the IAC, has participated not only in those two, but in all those. The red ones are the ones published, and the yellow ones are the ones that are works in progress. We have managed to publish already planets are 1.6 meters per second amplitude. We have two candidates are 90 centimeters. We have one candidate at Earth mass, and that's basically the limit of the field right now. We are there. This is the line that we cannot go below that line. But that's not where we want to go. That's what we have managed to go so far. We want to be there, which is the position in the diagram of Earth. That will be 10 centimeters per second, 365 days. And how we do that? Well, we need to up our game. We need to basically do everything better. The first thing is that we need to overcome some instrumental limitations because we lack RB precision. Our RB precision is limited to slightly better than a meter per second, and we want 10 centimeters. Our wavelength solution and drift monitoring is limited to 10 to 20 centimeters per second. We need it to be better also. And then we are also lacking photons. We are using 3-meter telescopes, and that allows us just to explore the very nearby solar neighborhood. So first thing is that we have already a new generation of spectrographs here. It's Espresso and Express. Espresso is the European one. It's a resolution over 100,000 spectrograph with a ultra high resolution mode over 200,000 and a low resolution mode of 70,000 that works using the 4 BLTs together as one telescope. It has a precision from 5 to 10 centimeters per second. 5, it's in the ultra high resolution mode, and also very, very bright stars. And then there's Express, that it's the American counterpart, that has an RB precision from 10 to 25 centimeters per second. It's not that mature yet. If you want to compare this with previous spectrographs, we are basically there. We started looking for exoplanets here with a precision around 10 meters per second, which was enough to detect Jupiter. Then with HARPS, we jumped below 1 meter per second, and we have been stuck at the 1 meter per second level for many, many years. And now with Espresso and probably with Express, we will be able to actually detect an Earth analog. At least the instrument, it's not going to be the limitation this time. Then we need to improve our wavelength solution and drift monitoring, and for that we're going to use, instead of thorium-argon or a Fabry-Perot etalon, we're going to use a laser frequency comb. A laser frequency comb, it's basically a laser that generates pools of equally spaced lines, and we can control the spacing and the wavelength perfectly. It allows for a much better wavelength solution and also much better drift monitoring. We already measured that we can do a drift monitoring between 1 and 2 centimeters per second. So again, the wavelength solution and drift monitoring, it's not going to be the limitation from now on. This laser frequency comb, by its nature, allowed also for a better characterization of the CCDs of the spectrographs. All spectrographs are built in this way. You have a big block that it's actually built using very small blocks. And what happens is that there are small gaps between the blocks, and you can have spectral lines in the gaps. And when the lines jump from one side of the gap to the other side of the gap, you get a few lines that cause a very huge change in velocity because you're having the wavelength of those lines wrong. It's usually just a few lines because there are just a few spaces, but the contribution can be around 1 meter per second, and it basically changes with the movement of the Earth. So you get a 1 year signal of 1 meter per second in all your data, which is not ideal. But using the laser frequency comb, we can monitor these gaps. We can measure the size of those gaps, and we can make a better wavelength solution that takes that into account. This is already been done, and there are already a few new discoveries with HARPs thanks to this, because basically we removed lots of noise that we were getting, and some very low amplitude signals started to appear. And then the last thing is that we need bigger telescopes, and we are solving it like basically just going to bigger telescopes. Espresso, instead of being in a 3.3 meters telescope, it's going to be at the BLT, and as I told you before, there's a low resolution mode of 70,000 that allows to use the 4 BLTs together as a single telescope. So once again, the telescope, it's not going to be the limitation now. But this was the, right now this is ready. The biggest problem is going to be, again, stellar activity. Because right now we don't want 1 meter per second, we want 10 centimeters per second, so everything is important now. The first thing is that, okay, these 300 meter per second rotation signals, these 10 meter per second rotation signals, we don't want them. We don't even want to deal with them. So first thing, it's the easy part. We are going to do a very, very strong preselection, and we are only choosing the best stars. So basically using the same relationships I showed you before, we can choose the slowly rotating stars that cause very small radial velocity amplitude, and we will only work with those. Then we will need to remove oscillations, and the best way to remove oscillations that happen around 5 minutes for the sun and different timescales for different stars is to really tailor the exposure times specifically to every star. There's already work submitted that estimated the ideal exposure time for every subspectral type in order to get to 10 centimeters per second. Here you get what happens in the sun depending on the exposure time, and if you go to exactly 5.4 minutes, you get the 10 centimeters per second you want, but then if you make it slightly longer, like, you get a worse contribution. You need to go to exactly twice 5.4 minutes, and then go down. Then for every star is different, so we will need to give every specific star its own exposure time designed specifically for that star. Then for granulation, we can do a bit of the same, and then we can actually model the granulation. Here we have two approaches. One's the brute force approach. That's basically we are going to bing a lot of exposures, because if we bing like 2 nights, 4 nights, 6 nights, 8 nights as a single point, we average the granulation. But the problem is that you lose all the sensitivity for maybe closing planets, and also you need a lot of nights of observation for this. The alternative is actually model the granulation. We can do magneto-hydrodynamic simulations of the surface of the star. We can construct a granulation profile and then try to reproduce it. We try to recover it using sun as a star simulations, and this is still a work in progress. This hasn't been tested in real data, but for now at least on simulations, it works on averaging the granulation below 10 centimeters per second. Then we have to go to rotation and cycles, and we have no other option than model them. There's no alternative. In this case, for rotation, we have our standard procedure that it's basically we predict what's going to be the rotation, we detect the rotation, we model it, and once we have like reasonably good parameters, we go one step further and we go to Gaussian processes. And this model includes a sinusoidal part, an exponential decay that represents the lifetime of active regions in the surface of the star, and then a noise parameter. And this is able to model even some very complicated stars. Still, it hasn't never been proved to 10 centimeters per second because that data does not exist yet. But it has been proved to less than half a meter per second in HARPS and HARPS North data. So this is right now our best path to model the rotation. And then for the magnetic cycles, the typical thing has been basically using a sinusoidal or a Keplerian to model the cycle, but there's a better way. We can model them basically, well, cycles usually cause a variation in radial velocity because they change the convective blue shift of the surface of the star. And that also changes usually calcium H and K, the calcium H and K contribution. So you can build a model that basically works with a correlation with the calcium H and K contribution and correlated noise also with the level of calcium H and K contribution. And you can subtract the contribution of the cycle. In this case, for example, using this kind of modeling, you get a 2 meters per second RMS reduction. And if you were to use like a sinusoidal to model the cycle, you will get an amplitude of around 2 meters per second. And the residuals will be worse. So we are reasonably confident that this way it's accounting for most of the stellar noise caused by the cycle. And with this, we finish with stellar activity. It should be, the tools are there, we just need to put everything together. But we still have one problem, that it's the problem with time series analysis, because we are still going to deal with very unevenly sampled time series, meaning we are going to have aliasing problems. We are going to, when you have multiple signals, you will have interference between the signals. As I said before, our Lomskargel periodogram assumes there's just one signal. And also, when we search for signals and we model them, there's some degeneracy between different parameters that can lead you to a wrong detection. First thing, for these two things, we need to take them into account together. There's no way of tackling them separately, so we need basically new techniques and a multi-signal approach. We need to assume that there are multiple signals from the beginning. New techniques are like, as an example, you have the L1 periodogram that was developed by Nathan Hara last year, that basically does a principal component analysis of the data. At the same time, it does a periodogram. It doesn't assume a number of signals. It assumes the number of signals can be anything, and it basically computes this periodogram, then measures the position of every peak, and it tries all the combinations between peaks under the assumptions that if the signals are created by planets, the final results has to be sparse, because most planets, like in the solar system, are very separated in period from each other. And then you can get something like this. This was the data from the radial velocity challenge that happened a few years ago, where people went to try different techniques. It was synthetic data, and it was this periodogram with these three real signals And if you look here at the traditional periodogram, you have a peak here, here, here. You have a lot of peaks that are actually just aliasing and a trend in the data. It's not planets. But with this technique, you manage to get these two very clearly, and this one, it's not that clear, but it's higher than all this forest of peaks. You can also go to multi-signal Lomscargle periodograms, where instead of just having one sinusoidal, you try combinations of several sinusoidals. This is basically an example, a very low resolution example of a two-dimension periodogram, where you have two signals that will be this one, and what you have, it's basically in color you have the significance, the yellow, the more yellow, the more significant, and then you have the period in the axis. This is the kind of thing that it's very computationally intensive, but still it can be quite easily done, and it usually has better results than the traditional Lomscargle when there are multiple signals, that it's most of the times. You can always go to genetic algorithms that basically are a very computationally cheap way of exploring large parameter spaces, where you basically define a model and you define a set of initial parameters that can be as broad as you want, and then you test the chi-square or whatever indicator you want of all the combinations, and you save the best ones, and then you make those best ones have kids together. Basically, you mix the parameters, and then you also mutate some of them, and you create a new family at the beginning that it's as big as the one, and you try again, and you try again until you satisfy a convergence criteria. And this usually it's very, very powerful at detecting multiple signals in the data. It also, it's very quick at doing some things like simultaneous modeling of different time series. In this case, for example, you have the 3 time series of radial velocity, calcium H&K and H alpha, and what I did was model them together as one thing with the period that you see here. It's the magnetic cycle. I used one single parameter for both. I was minimizing it for the 3 at the same time, and there are also some other parameters fit together, and it basically can help you distinguish between stellar signals, planetary signals. If you give it like photometry and radial velocity and you have the rotation and one planet, if you give one shared parameter between the two, it's going to find the rotation in both at the same time, and then the other one, it's going to be the planet. And then the last one is that we need to be very careful with this, because we have a problem with eccentricity. Eccentricity in most radial velocity detection and modelings is overestimated, because it's super easy to overestimate eccentricity. Here you have this is synthetic data, and that's what happens when you have this is the real eccentricity. If you have like the wrong noise model, for example, for your data, you are going to overestimate the eccentricity. If you have a second planet that you are not accounting for because you don't know it's there, the eccentricity is going to do whatever. It's going to go really high, really low. If you have basically the model is too complex, you are going to overestimate the eccentricity. This is basically a problem when then estimating masses and habitability, because eccentricity is pretty important, but there's an easy way out. Usually chi-square modeling is very sensitive to this effect. It tends to overestimate eccentricities, but Bayesian MCMCs are usually have the opposite effect. They tend to penalize high eccentricity, because even if you keep the same number of parameters, high eccentricity is a more complex model. And usually this kind of fitting always favors the simplest model possible. So lesson here is that for the final modeling of the system, this is mandatory all the time. We cannot just rely on chi-square modeling, even if it's quick and very easy to apply. And with all this, next thing we need to check is that actually our different ways of measuring and detecting and modeling planets, set Bayesian MCMCs, Gaussian processes, genetic algorithms, chi-square periodograms, give us the same result. No one's going to believe an Earth-like planet that only appears with one method. That's clearly not going to happen. But luckily, there was a study, this is wrong, it's 2018, it's from a few months ago, where they tested on synthetic data the results of many different algorithms. And the good thing was that basically most of them agreed on when there was a planet and when there wasn't a planet. That doesn't mean most of them had it right, but they agreed on the result. Main difference was that the frequentist, the non-Bayesian analysis were usually very aggressive. When they said there was a planet, they said there's a planet for sure. When they say there's no planet, they said there's totally not a planet. While Bayesian methods are, there might be a planet, there might not be a planet. They are never so aggressive in the conclusions. But the good thing is that even the quick methods give reasonably good results. So it's good enough that you can work with the computationally cheap ones, get your results, and then go to the computationally expensive ones to confirm the results. You don't need to start with these ones that might need a week or two for the initial modeling. And once you have all these instruments are in place, we have the techniques to model the stellar activity, we have the techniques to model the time series, we are ready. Well, I mean, it's going to be really hard because no one has done all that for a single system. That has never happened. But we at least know what we need to do. We just need to get all the tools that we have, that many groups have developed, and we need to put them together and make that the standard procedure, do everything all the time. So it's going to be hard, but we know how to do it. And now I'm going to just leave you with a small summary and a picture of my cat. Thank you.
Time for questions? We have plenty of time.
First of all, thanks for the interesting talk. I really like it. And now we know how difficult it is to deal with stellar activity. And the question is, once you detect a preliminary candidate of exoplanet, do you change the observational strategy taken by HARPS or HARPS North? Let's taking 1 or 2 measurements per night, or I don't know, depending on the period of the planet, of course.
Usually what we do once we have a candidate is we double down of the observation of that star. We get more data on that star. Sometimes 1 or 2 measurements per night, even 3 sometimes, because that helps with granulation. And it reduces the noise, and basically it allows you to boost the significance really quickly. And once we have a significant detection, ideally we go back to the telescope and we do it again to check that it's still there, that it doesn't go away, that we are not in we don't want our candidate to do this. So we need to go back and check that it's not doing that it keeps, the significance keeps going up.
Hi, Alejandro. Nice talk. Just a comment. I would like to hear your opinion. Now you're facing 10 centimeters per second, and as you said, you started to do this 14 years ago. when you were at school, right? The group, and it took 14 years to get a 1 meter per second signal on a super Earth. Now we go to 10 centimeters per second, and we have to deal with the same signals and all additional signals, which are between 10 centimeters per second and a meter per second. So I bet even with all this modeling, you'll still need not a 14 but a 28-year long time period. And now we are on a 10-meter telescope, which is not the same situation as all these surveys have had with a 3-meter telescope with hundreds of nights a year. So how do you see this scenario? And you're going to compete now with TESS providing really bright targets amenable for characterization. How are you going to choose your targets with the few time you're going to have? Well, for example, the GTO has only 5 years, which is not enough for a super Earth on a 300-day orbit. How are you going to choose this sample at the beginning to be able to, in 10 years, 15 years, publish an Earth-like planet?
The first thing we are going to do is basically choose fewer stars than the previous surveys had, so we can concentrate on the stars. So the preselection phase, it's incredibly important right now. Also, most of the stars that Espresso is going to do are not going to be new stars. They are going to get all the HARPS measurements. So many of the effects, in the cycle, the rotation, we are going to at least know where it is, what's the amplitude. And of course, TESS is going to detect probably much more planets than Espresso, but like by an orders of magnitude. But I'm not sure TESS is going to be able to find what we are looking here, because the strategy of TESS is like, it's really far from... No, but yeah, the idea from now on is just to concentrate in a very small number of targets. So probably first year it's going to be used to select the best targets, and then you go with a few. And you go from day one doing a few observations per night, you concentrate them as much as you can, you keep doing complementary observations with HARPS and HARPS North, and basically you try to take all the information that you can to clean the data from stellar effects, and then use the Espresso one just for the low amplitude signals. But it's going to be really, really hard. The first estimations were that it was possible to find an Earth-like planet in 4 years, but that's probably not going to happen. That's really optimistic, but that's the goal. That's the goal. Take at least one of the stars. It's going to be observed every single campaign, every single day that the GTO has time, for 4 years, and it's never going to stop until they have it.
Okay, more questions?
Thank you for a very nice talk. You have mentioned the MHD simulations as a tool to quantify the granulation in the stars. I wonder what kind of simulations they use and how critical they are. I mean, how are they customized for the star in question, or?
Right now, basically, they are simulations of the sun as a star, not still not customized for different spectral types, because actually it's really hard to... We don't really know how is the surface of stars that are not the sun. We know very few, very little of that, especially if you move to M dwarfs, that's... So at least for now, the MHD simulations are going to be used only for solar twins, basically. But for, as far as I know, because that's not my area of expertise, in K dwarfs, the granulation is expected to be a smaller problem than in solar type stars. So maybe we are good enough just beaming 2-3 nights for K dwarf, because also in a K dwarf we don't need 10 centimeters per second, we need 20. And if we go to an M dwarf, we need half a meter per second. The 10 centimeters is the final goal for Earth 2, but the realistic goals are the K dwarf and the M dwarf.
Okay, thanks. Any other question? Okay, on my own. It's really impressive, all these biases that you had to compensate, to get rid of, to go to achieve your goals. So, and my background is on solar physics. And from day one there, you learn that different spectral lines behave differently in the way they shift according to granulation or assumption or whatever. So you hadn't mentioned that a way to really separate what comes from a planet and what comes from the star could be simply using different combinations of spectral lines. You're detecting the whole spectrum, right?
Yes.
Simultaneously. So by separating, by using different spectral lines, in principle you can separate what comes from a planet and what comes from the star. So could you comment on that?
Well, actually, I should have talked about that because I forgot. There's already a project by Xavier Dumusque from the Observatory of Geneva of using, right now it's only on alpha cen B, using machine learning techniques to select the best lines of the 9,000 that we use for the radial velocity, to use the ones that correlate less with the calcium H and K. For now it's for rotation mostly, and the preliminary results are that you can, if you take all the spectrum, you get a rotation signal of around 2 meters per second. If you get the most affected lines, you get a rotation signal of 10 meters per second, and if you choose the 1,000 less affected lines, there's no rotation signal. So that's something that you can do, but it has some problems. First, you need a lot of data before selecting the lines, because we already know that for alpha cen B and alpha cen A, the list of lines is not the same and not compatible. You need to do it for every star one by one. And then you need a very high signal to noise. If you go to a magnitude 9 star, you cannot do it, because when you move to 9,000 lines to 1,000 lines, your radial velocity precision moves right now from 1 meter per second to 5 meters per second. You can do it on magnitude 0 stars, 1, 2, 3, but just those. But that's also going to be done for sure. But it's not a short-term thing.
So, I mean, thanks. And I mean, it's kind of very natural that you are using that piece of information, because it's very valuable. About the selection of lines, I mean, this is not black magic. It all depends on the stratification of the atmosphere of the star. So whether you have convection, how high it reaches, etc. So weak lines are expected to be formed deeper down, and the cores of very deep lines are expected to be something in the upper parts, which are less sensitive to things like granulation. So in principle, this can be worked out in theory without a big effort, I guess.
No, that's how the masks were built in the first place, but that's not enough. I mean, in this case, the idea was to basically have lines that are not affected in any way by the stellar activity, and there are not that many that are not affected in any way.
Okay. Any other question? So if not, let's thank the speaker again. And